When running multiple conduits from a load center to a junction box, the question arises whether a single equipment grounding conductor, or EC, in one of the conduits can serve all the circuits leaving the junction box. The answer is yes, under certain conditions outlined by the National Electrical Code, or NEC. The NEC addresses scenarios where multiple circuits are installed in the same raceway, cable, or enclosure. When dealing with multiple conduits, each containing circuit conductors, a key requirement is to ensure that the equipment grounding conductor is adequately sized to handle the available fault current for all circuits it serves. This means the single EGC within one conduit must have sufficient ampacity to safely carry the ground fault current from all the circuits originating from the junction box. To determine the appropriate size of the equipment grounding conductor, refer to NEC Table 250.122. This table provides minimum sizes for equipment grounding conductors based on the rating or setting of the overcurrent protective device in the circuit. When using a single EGC for multiple circuits, the size must be based on the largest overcurrent protective device protecting any of the circuits served by the TGC. For example, if you have 3 circuits rated at 20 amps, 30 amps, and 40 amps respectively, all originating from the junction box and utilizing a single EGC in one of the conduits, the EGC must be sized according to the 40 amp overcurrent device. The equipment grounding conductor must be installed in accordance with NEC section 250.130, which covers the methods for connecting equipment grounding conductors. The connection points must be secure and provide a low impedance path for fault current to return to the source. This ensures that in the event of a ground fault, the overcurrent protective device will trip quickly, minimizing the risk of electrical shock or fire. Consider the physical protection of the equipment grounding conductor. It should be installed in a manner that protects it from physical damage. Since it is located in one of the conduits, it inherently has a level of protection. However, ensure that the conduit itself is properly supported and protected as required by the NEC. When dealing with metal conduits, the conduit itself can serve as the equipment grounding conductor if it meets the requirements of NEC section 250.118. This section specifies the types of metal raceways and enclosures that are suitable for use as equipment grounding conductors. The metal conduit must be electrically continuous and have low impedance to ground. This is typically achieved through proper installation of listed fittings and connectors. Where non-metallic conduits are used, a separate equipment grounding conductor is always required within the conduit. The EGC must be identified with a green color or green with one or more yellow stripes, in accordance with NEC section 250.119. This ensures that it is easily distinguishable from other conductors within the conduit. Consider the length of the conduits and the potential for voltage drop on the equipment grounding conductor. Long runs can increase impedance, which can reduce the effectiveness of the grounding system. In such cases, it may be necessary to increase the size of the EGC to compensate for the increased impedance. Grounding electrode conductor, or GEC, connects the grounding electrode to the equipment grounding system. It is a crucial part of the overall grounding infrastructure. The size of the GC is determined by NEC Table 250.66 based on the size of the service entrance conductors. The equipment grounding conductor must be connected to the grounding electrode system at the service equipment or at the source of a separately derived system. This connection provides a path for fault current to return to the source, allowing the overcurrent protective device to trip and clear the fault. Also, remember that all metal enclosures, such as junction boxes and cabinets, must be properly bonded to the equipment grounding system. This ensures that any fault current on the enclosure will be safely conducted back to the source, minimizing the risk of electrical shock. Bonding is typically achieved using bonding jumpers, which are conductors that connect the metal enclosures to the equipment grounding conductor. The size of the bonding jumpers is determined by NEC Table 250.102. When working with sensitive electronic equipment, it may be necessary to provide supplemental grounding to minimize electrical noise and interference. This can be achieved by installing additional grounding conductors and bonding the equipment to a dedicated grounding electrode system. Ensure that all grounding and bonding connections are made with listed connectors and fittings. These connectors are designed to provide a reliable and low-impedance connection, ensuring the effectiveness of the grounding system. Consider the environmental conditions in which the electrical installation is located. In corrosive environments, it may be necessary to use corrosion-resistant materials for the equipment grounding conductor and bonding jumpers. This will help to prevent corrosion and ensure the long-term reliability of the grounding system. Also, remember that the equipment grounding conductor must be accessible for inspection and testing. This allows for periodic verification of the integrity of the grounding system. Inspections should be conducted regularly to ensure that all connections are tight and free from corrosion. During the design phase of an electrical installation, carefully consider the grounding requirements and select the appropriate size and type of equipment grounding conductor. Proper grounding is essential for electrical safety and helps to protect against electrical shock and fire hazards. Before making any changes to an existing electrical installation, consult with a qualified electrician or electrical engineer. They can provide guidance on the applicable codes and standards and ensure that the installation is safe and compliant. The NEC is updated every 3 years, so it is important to stay current with the latest requirements. This will help to ensure that all electrical installations are safe and compliant with the latest standards. When working with electrical systems, always follow safe work practices. This includes wearing appropriate personal protective equipment, such as gloves and eye protection, and energizing circuits before working on them. Also, ensure that you have a thorough understanding of the electrical system and the potential hazards involved. One must ensure that the equipment grounding conductor is continuous and effectively connected to all metal parts of the electrical equipment. This includes enclosures, raceways, and other metal components that could become energized in the event of a fault. The continuous connection of the EGC provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protective device to trip and clear the fault. Proper labeling and identification of the equipment grounding conductor are crucial for safety and maintenance. The EGC should be clearly identified with green insulation or green tape at all termination points. This helps to prevent accidental disconnection or misidentification of the EGC. Also, ensure that all electrical panels and enclosures are properly labeled to indicate the location of the grounding electrode system. Regular inspections and testing of the equipment grounding system are essential for maintaining its effectiveness. Inspections should include visual checks of all grounding connections to ensure that they are tight and free from corrosion. Testing should include measurements of the grounding impedance to verify that it is within acceptable limits. If any deficiencies are found during inspections or testing, they should be corrected immediately. When installing or modifying an electrical system, always follow the manufacturer's instructions for grounding and bonding. The manufacturer's instructions may provide specific requirements for grounding and bonding that are not covered in the NEC. Failure to follow the manufacturer's instructions could void the warranty on the equipment and could create a safety hazard. Also, remember that the equipment grounding conductor must be sized to carry the available fault current. The available fault current is the maximum amount of current that could flow in the event of a short circuit. The size of the EGC must be large enough to safely carry this current without overheating or causing damage to the conductor. The available fault current can be calculated using engineering software or by consulting with a qualified electrical engineer. Furthermore, be aware of the potential for ground loops in electrical systems. Ground loops can occur when there are multiple paths for ground current to flow. This can create unwanted noise and interference in sensitive electronic equipment. To minimize the potential for ground loops, it is important to use a single-point grounding system. In a single-point grounding system, all grounding conductors are connected to a single grounding point. When working with older electrical systems, it is important to verify that the grounding system is adequate. Older systems may not have been designed to meet the current NEC requirements for grounding. If the grounding system is not adequate, it should be upgraded to meet the current requirement. Also, consider the impact of harmonics on the equipment grounding system. Harmonics are non-sinusoidal waveforms that can be generated by electronic equipment. Harmonics can increase the current flowing in the EGC, which can lead to overheating and damage to the conductor. To mitigate the effects of harmonics, it may be necessary to use a larger EGC or to install harmonic filters. Finally, remember that the equipment grounding system is an essential part of the overall electrical safety system. A properly designed and installed grounding system can help to protect against electrical shock and fire hazards. By following the NEC requirements for grounding and bonding, you can ensure that your electrical system is safe and reliable. When dealing with isolated ground receptacles, it is essential to understand their purpose and proper installation. Isolated ground receptacles are designed to reduce electrical noise and interference in sensitive electronic equipment. They have a separate grounding conductor that is isolated from the normal equipment grounding conductor. The isolated grounding conductor is connected directly to the grounding electrode system, providing a dedicated path for ground current to flow. However, when you have a multi-wire branch circuit, the neutral conductor carries the unbalanced load current. The neutral conductor must be sized to carry the maximum unbalanced load current, which is the difference between the currents and the hot conductors. The NEC specifies the minimum size for the neutral conductor based on the calculated unbalanced load. Also, in industrial settings, it is often necessary to install cable trays to support electrical cables. Cable trays must be properly grounded to prevent electrical shock hazard. The cable tray can serve as the equipment grounding conductor if it meets the requirements of NEC section 392.60. The cable tray must be electrically continuous and have low impedance to ground. This is typically achieved through proper installation of listed fittings and connectors. When dealing with underground electrical installations, it is important to protect the equipment grounding conductor from corrosion. Underground EGC should be made of corrosion-resistant materials such as copper or stainless steel. They should also be installed in a manner that protects them from physical damage. Also, consider the use of ground fault circuit interrupters, or GFCIs, in areas where there is a high risk of electrical shock. GFCIs are designed to detect small ground faults and quickly to energize the circuit. They are required in bathrooms, kitchens, and other areas where water is present. Furthermore, be aware of the requirements for surge protection in electrical systems. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning or other events. SPD should be installed at the service entrance and at other critical locations throughout the electrical system. In healthcare facilities, it is essential to provide a reliable and redundant grounding system. Healthcare facilities have stringent requirements for grounding to protect patients and staff from electrical shock hazards. The grounding system must be designed to minimize the potential for voltage differences between different pieces of equipment. In addition, in hazardous locations, such as those where flammable materials are present, it is essential to use explosion-proof equipment and wiring methods. Explosion-proof equipment is designed to contain any internal explosions, preventing them from igniting flammable materials in the surrounding environment. The NEC specifies the requirements for explosion-proof equipment and wiring methods in hazardous locations. Furthermore, be aware of the requirements for arc flash hazard analysis. Arc flash is a dangerous electrical phenomenon that can occur when there is a short circuit in an electrical system. Arc flash can cause severe burns and other injuries. An arc flash hazard analysis should be conducted to determine the potential arc flash hazards in an electrical system. The results of the analysis can be used to select appropriate personal protective equipment and to develop safe work practices. Also, consider the use of energy-efficient electrical equipment and lighting. Energy-efficient equipment and lighting can help to reduce energy consumption and lower utility bills. When selecting electrical equipment and lighting, look for products that are ENERGY STAR certified. Finally, remember that electrical safety is everyone's responsibility. By following safe work practices and by being aware of the potential hazards, you can help to prevent electrical accidents and injuries. If any doubt exists, consult a qualified electrician.